Every aircraft flying today has round windows. Not because they look better, not because they're easier to manufacture, because square windows killed 56 people and the industry spent 2 years figuring out why. The de Havilland Comet, the world's first commercial jet airliner, broke apart in mid-air 3 times in 18 months. The investigation found the cause at the corner of a window, a geometric shape, not a mechanical failure, not a design error anyone had thought to check. A corner. To understand why a corner destroys an aircraft, you need to see what pressurization does to the fuselage skin on every single flight. In May 1952, the de Havilland Comet entered commercial service with BOAC and changed what aviation meant. Before the Comet, commercial flight was propeller-driven, slow, and loud. Transatlantic crossings took the better part of a day. Passengers endured vibration, noise, and the particular discomfort of piston engines operating at their limits for hours at a stretch. The Comet flew faster, higher, and smoother than anything preceding it. Jet engines at altitude produce less vibration and dramatically less noise inside the cabin. The aircraft cruised at 35,000 feet, where the air was thin and the ride was steady. It was, by every measure available in 1952, the future of commercial aviation. Britain had built it first. That fact carried significant national and industrial weight. The first sign that something was wrong came in May 1953, when a Comet broke apart during climb-out from Calcutta in severe weather. The loss was attributed to the storm. Aircraft had been lost to extreme weather before. The investigation did not penetrate deeper than the immediate circumstances. In January 1954, BOAC Flight 781 departed Rome's Ciampino Airport, climbed to cruising altitude over the Tyrrhenian Sea, and broke apart at 27,000 feet. 35 people were killed. The wreckage fell into the Mediterranean. Recovery of debris from depth took months. The Comet fleet was grounded, inspected, and returned to service after modifications the investigation had suggested as precautionary measures. The cause remained officially undetermined. In April 1954, South African Airways Flight 201, operating a leased Comet, broke apart near Naples under nearly identical circumstances. 21 people died. The fleet was grounded permanently. This time, the investigation did not stop until it had an answer. The Royal Aircraft Establishment at Farnborough took the lead. The investigation's central challenge was that the primary wreckage was on the floor of the Mediterranean at depths that made comprehensive recovery impossible. The investigators had to determine the failure sequence from partial evidence recovered fragments, witness accounts from other aircraft, and the physical evidence that wreckage yielded about the sequence in which the structure had separated. What they established was that the aircraft had failed in flight, not on impact. The structural separation had occurred at altitude, under normal flight loads, without any external cause. The aircraft had not been struck. It had not encountered extreme weather. It had broken apart under conditions it was certified to survive. That conclusion made the investigation a structural problem, not an operational one. The RAE constructed one of the most significant experimental investigations in aviation history. A complete Comet fuselage was placed inside a water tank at Farnborough and subjected to repeated pressurization cycles. The fuselage was filled with water, pressurized to simulate cabin pressure, then depressurized thousands of times in sequence. Water was used instead of air deliberately. A pressurized air vessel that fails releases its energy explosively. A pressurized water vessel that fails releases very little energy. The liquid is nearly incompressible and doesn't expand violently. Using water meant the test could be conducted safely to failure, with the investigators present to observe exactly where and how the structure cracked. The fuselage cracked at the corner of a window aperture. Within a fraction of the cycles the actual aircraft had accumulated in service before its failures, the test article reproduced the cracking that had destroyed the operational aircraft. The location was unambiguous. The mechanism became clear. A pressurized fuselage behaves like an inflating cylinder. The internal pressure pushes outward against the skin in all directions. The skin carries that load in tension. It is being stretched, slightly, on every flight. When a cutout interrupts that skin, a window aperture, a door frame, Any opening, the stress that was flowing through the material that is no longer there has to go somewhere. It redistributes around the opening, flowing along the edges of the cutout the way a river flows around an island. At a smooth curve, that redistribution is gradual. The stress increases approaching the curve and decreases, leaving it, but the transition is continuous and the peak value remains manageable. At a corner, a sharp change in direction, the redistribution cannot be gradual. The stress attempting to flow around the corner has nowhere to go smoothly. It concentrates at the corner point. The mathematical stress concentration factor at a sharp square corner in a loaded plate is approximately 3. That means the stress at the corner of a square window is approximately 3 times higher than the stress in the surrounding skin. Not 3 times higher after some weakening process. 3 times higher on the first pressurization cycle. 3 times higher on every subsequent cycle. Aluminum under repeated stress cycles doesn't fail immediately at stresses below its ultimate strength. It develops microscopic cracks at the location of highest stress. Those cracks are invisible to external inspection in their early stages. They grow with each cycle incrementally, by fractions of a millimeter per pressurization. The growth rate accelerates as the crack lengthens, because a longer crack concentrates stress at its tip more severely than a shorter one. At a critical crack length, the remaining uncracked material cannot carry the applied load. The failure is not gradual at that point. It is instantaneous. The skin separates, the pressure difference between the cabin and the outside air acts on the new opening, and the structure fails progressively and rapidly from that initiation point. The Comet hadn't been weakened by anything that happened to it. It had been weakened by everything that was supposed to happen to it. Every normal flight had advanced the crack. The corner was a corner from the first day it flew. The cause was a corner. The fix was a curve. But implementing that fix required rebuilding every assumption about how aircraft were designed, tested, and certified for passenger service. The geometry of the solution was the simplest part of what the Comet investigation produced. A curved aperture eliminates the mechanism that destroyed the Comet. When stress flows around a smooth ellipse or circle, it has no corner at which to concentrate. The redistribution is continuous around the full perimeter of the opening. The stress concentration factor for a true ellipse approaches a value close to unity, meaning the peak stress at the window edge is comparable to the stress in the surrounding skin rather than a multiple of it. The window edge is still a stressed location. It is not a catastrophically stressed location. The transition from square to round is not a binary switch. Corner radius is a continuous variable, and the stress concentration factor decreases as that radius increases. A window with slightly rounded corners is better than a window with sharp corners, but still carries a meaningful concentration factor. A fully elliptical window carries almost none. The design objective is not simply to avoid sharp corners, it is to maximize the corner radius within the geometric and structural constraints of the window location and the fuselage frame spacing around it. Contemporary aircraft, windows are not circles. They are vertical ellipses, taller than they are wide, with the long axis aligned vertically between the fuselage frames that define the structural grid of the cabin section. That orientation is not arbitrary. The primary hoop stress in a pressurized cylinder, the stress that acts circumferentially around the fuselage, is twice the axial stress that acts along the fuselage length. Orienting the long axis of the window ellipse perpendicular to the dominant stress direction minimizes the stress concentration the aperture introduces into the highest loaded direction of the skin. The window shape is optimized against the stress field it sits in, not against any aesthetic preference. The corner radius of every certified commercial aircraft window is a regulated engineering parameter. It has a minimum value derived from fatigue analysis of the specific aircraft structure, demonstrated through physical testing and recorded in the aircraft's certification basis. It is not a style decision. A manufacturer cannot reduce the corner radius because a customer prefers a different window shape. The geometry is fixed by the certification evidence. This certification evidence, the requirement to demonstrate fatigue life through physical testing rather than simply calculating static load capacity, was the second and more consequential output of the Comet investigation. Before 1954, commercial aircraft were certified primarily against static requirements. Could the structure carry the design ultimate load without failing? If yes, the structure was certified. The possibility that repeated sub-ultimate loading could initiate and grow cracks to failure metal fatigue under pressurization cycling was understood as a phenomenon in engineering literature, but had not been incorporated as a formal certification requirement for commercial aircraft structures. The Comet investigation made that incorporation mandatory. The RAE water tank test was not just a diagnostic tool for understanding the Comet failures, it was the demonstration that fatigue testing of pressurized aircraft structures was both necessary and technically feasible. The regulatory response in Britain through the airworthiness requirements for civil aircraft and subsequently incorporated into the emerging international standards that would become the basis for FAA and EASA certification frameworks established that every commercial aircraft must demonstrate fatigue life through physical pressurization cycling of the airframe before it enters passenger service. The specific requirement that emerged was conservative by design. Test articles must accumulate pressurization cycles significantly exceeding the aircraft's intended service life, with periodic inspections for crack initiation and growth before certification is granted. The safety margin between the demonstrated test life and the certified service life provides the buffer within which operational cracks initiated by damage, manufacturing variation, or operating conditions can be detected and repaired before they reach critical length. The investigation also revealed a secondary failure mode that the initial focus on window corner geometry had not immediately surfaced. The method used to attach the Comet's window frames to the fuselage skin introduced additional stress concentrations at the fastener holes around the window perimeter. The punching process used to create those holes rather than drilling had left residual stresses in the material around each hole that compounded the corner stress concentration. The crack that destroyed the aircraft had initiated not just at a corner but at a fastener hole. At a corner, the combined effect of two stress concentration sources acting at the same location. This discovery expanded the investigation's implications beyond window shape. Any mechanical fastening in a fatigue-critical location, rivets, bolts, any fastener hole is a potential crack initiation site. The design and manufacturing requirements for fatigue-critical fastener installations in pressurized aircraft structures emerged directly from the Comet investigation and remain embedded in aircraft manufacturing standards today. Hole preparation methods, fastener fit tolerances, and installation processes in fatigue-critical locations are regulated at a level of detail that traces its origin to the Farnborough water tank and the cracks it found. The aircraft that flies you from one city to another today was certified against a fatigue demonstration standard that didn't exist before 1954. Its windows are elliptical because a concentration factor of 3, applied to a square corner, was applied to the Comet on every flight it ever made. Its fastener installations and pressurized skin panels follow manufacturing standards developed because a punched hole at a window corner compounded a stress that was already 3 times what it should have been. Every round window on, every aircraft flying today is the answer to a question 3 crashes asked simultaneously. The answer was geometric. The implications were everything else.